So back to the how much does she drink and what is what? Okay, well, if we look at that lesson master on the first question, should I project it for you?
Sure.
Would that be easier? Okay. Maybe then we can all point at that and know what we're talking about for sure. I think that the first question does a lot to set the stage and make it so that we can then just fall right into answering the questions. Because, let me, I said a lot yesterday and some of it might have gone really, really fast. And if you don't slow me down, by now you gotta know that I just go faster, right? At least I try not to, but I do. So, this basic idea that if we have a length which is 1D, and we multiply it by, like we make it 5 times as long, we just take that and we multiply by 5. You're okay with that?
Yeah.
Okay, good. So that's just K. That's what we call K in the similarity theorem, the fundamental theorem of similarity. K is this constant, it's the size change factor, multiplier. But if you go to 2 dimensions, like area, you've got pi r squared, so you have there's a length that gets to the second power. Here you would have a length that's taken to the second power. So if we say we're going to double these dimensions with the number k, we gotta multiply that one by k, we gotta multiply that one by k, so then it ends up being kx squared. So we have to use a size change factor that's squared when we're talking about area. Are we okay with that one? Yeah. You guys okay with that one? And then when we go to volume, and we start out, and we say, well, this is x by x by x, because it's length times width times height. Any volume is measured this way. I mean, the cube is the real easy shape to work with. But you can have a sphere, a sphere, a ball, and that's 4/3 pi r cubed. Again, there's a length which is taken to the 3rd power. There's a volume then, it's a sphere. The cube is the same way. There's a length that gets taken to the 3rd power, or maybe even these are different numbers, like 3 and 4 and 5 on that first thing that you guys did. And if we say that we're going to make each of these a certain number of times longer, then you've got k times that, k times that, k times that. If it's this, then you have k times r, which is to the 3rd power. So what you end up with volumes is, if you know your size change factor, your calculations get done with that size change factor to the 3rd power. So then question number 1 here is really important. Because what this does is it allows us to identify which k value we use for all of the different things in these problems. So what we're supposed to do is we're supposed to arrange these by length, area, and volume. Length, area, and volume. And here, length is going to get a k. Oh shoot, nothing's lined up, dang it. Maybe if I just close my eyes. There we go, k squared and k to the 3rd power. No, I can't write on there, I don't know. Oh, I know why it's not lined up. If I move this one way or the other. Pretty close. I was messing with it. We got new smart boards. And we were thinking we were going to hang one on here until it came down that Mr. Baumgartner and I going and taking one of the smart boards, and we were going to take it off of the pallet, the new ones. And we went to lift it up, and we lifted really, really hard, and it didn't even come off of the pallet. So we said, no, it's going to be too heavy for this thing. They're like wicked, wicked heavy. They're the ones like Van Wise and mine, these are that much bigger. They're just huge. Diagonally, they're 15 inches bigger. So they make massive smart boards. Anyway, pint, length, area, volume. Is a pint a volume, a length, or an area? It's a volume. What's a meter? What's a mile? In a square centimeter? Whoops, what am I doing? I'm writing in the wrong place. This is a meter. This is a mile. This is a square centimeter. Ounces. You know, I don't think that they're mass. I think that they're volumes of liquid. But even if they're not, then ounce is still going to be third power, because weight's going to be that way as well. So then we've got an acre, or no, a liter, I'm sorry. Liter is a volume. What's an acre? Area of land. And a kilogram? Yeah, that's going to come up as a volume. It certainly isn't a length, and it certainly isn't an area, and it's going to be a third power because it's a particular mass. So, with that in mind, you get down to orange juice. When this person's body size changes, and then we have to say how much their intake of orange juice is going to change, we have to use that K to the third power. So where, is this it here? This will give it to us, right? So how tall she's going to be, what are you going to use for K? 6. Good. For her weight, what are you going to use for K? 6 to the third, 216. So the amount of orange juice that she's going to need would also be 6 to the third. I think it's because you can think of it, you know, your nutrition that goes into your body is going to be the same as, or to be relative to or proportional to your weight. So if your weight's going up by 216 times, you're probably going to need 216 times as much liquid. You can do number 4.
For 4B, I did the stations and it came out really,
Okay, so if she's a sixth as big, what K value do you want to use for her height?
1/6
For her height? Yeah, but let's just stick with how tall she would be. It'd be 1/6 of 5 feet. So it'd be like 5/6 of a foot? And so that would be how many inches? Did anybody get that far? 10 inches, yeah. So her height is 5/6 of 5 feet. That's going to end up being, no, I'm sorry, her height is 1/6 of 5 feet. 1/6 of 5 feet is going to be 5/6 of a foot, which is 10/12 of a foot, which is 10 inches. Okay, so her weight, which of the K values do we want to use for her weight? K squared, K to the first, K to the third. Which one? Third for her volume. So if K is given, or the size change is given as 1/6, yeah, we got to use 1/6 of 1/6 of 1/6, which is 1/216th. 1/216th of 100 pounds. Yeah, so you got the 100 pounds, it's a weight, and we're saying that this person is 1/6 of their original size. And I know that what makes this one hard, I think, or this concept hard, is that we're so used to thinking of Oh, well, they're half as big because they weigh half as much. And I think what we have to do is be careful about what we're saying. You remember when I said early in the year, I said geometry is gonna have so many things where the vocabulary is really precise and really exact. And that's gonna be a challenge for us because of how we speak and communicate to one another normally. You know, English language and any spoken language has its own way of kind of having meanings evolve and meet the needs of the time. And you know, here we are living in 2021 and we use words certain ways and we structure our sentences in certain ways that are not good English. They're actually very poor English. If you sat in a class in Europe and you were learning to speak the English language, you would not be learning to talk the way we do. Yeah? Where did you learn how to speak English?
Well, English was my first language.
That's your first, okay. So then but you learned Thai from your mom. Okay, shoot. What about people over there that learn English in Thai schools? You ever talk to them about what their English is like?
I haven't, but I know that my mom took English classes.
Yeah, your mom had to learn English there, because Thai's her first language.
And since a lot of like people from America come there, a lot of the business owners know English, and a lot of the people there know English.
Yeah. I've talked with kids from European schools and such, and they say that what they learn is so much different than what they experience when they're here. And if you think about foreign exchange students that we've had that come from non-English speaking countries, when they're here, at first their English is very, very structured and blocky sounding. It doesn't flow, because that's how they learn it. But then, once they're here for a while, it changes. Well, geometry is stuck with these old meanings and these old ways of structuring descriptors. And this is an example of it. We talk about a person half as big and we're thinking about half of the weight. But in this case here, we're talking about a particular size, which is said to be 1/6 as large. So 1/6 of the height, 1/6 of the width, 1/6 of the depth turns into 1/6 cubed. So this ends up being 1/216 times 100 pounds. So you've got 100 over 216. So it's approximately a half a pound. Yes.
So the equation that I've been working with, and the one that I thought you had said was like k times whatever you're changing to the third power. So it'd be like in parentheses to the third. So you'd be like cubing the 100 pounds as well.
No, you would not. Here, this, to come up with the actual, ooh, now I see where you're going. Oh, yes. I see, okay. Now I understand what you and Joan were talking about yesterday and the disconnect here. Okay. Do you understand what she's saying? Because okay, what Mary's saying is she thinks because this is sort of like the X value, it's like your original amount, that you would do 1/6 times 100 to the third power. But that's not correct, and let me explain why. And here's the disconnect. This is good. I'm glad I'm catching this. Where does that number 100, conceptually, where does it come from in terms of my x's over here?
A length,
What?
like a length.
It's like a length, but a length, it's already turned into a volume. Yeah, so this is already, even though it's not a volume, it's already thought of as a volume that we involve the third power with. So if for example, we were talking about a particular cube, and that cube was 100 units by 100 units by 100 units, then it would already be 100 to the third power. And then if I went and I made this 5 times as long, and I'd make it 5 times as long in every direction, then I would have this going on. But see, this is the original volume taken to 5 to the third, or k to the third times. This is the original volume, even though it's a weight. So we don't have to take that number to the third power because it already came from something that was a third power. Does that help?
Yeah, so if you're
Good.
like multiplying the size change factor and it's greater than 1, do you keep it in that bracket when you do the k times x to the square? Or is it just you always do k squared cubed times 2?
Well, you would not include it in a power if you already knew the original size.
So like if you're inflating it, then you have to put it in parentheses? You do like kx times kx squared.
Mm-hmm. But if I already knew what x squared was,
How can you tell, how do you know what it is? Like what,
maybe on the back side we would know. So our orange juice is gonna be 1/216th of it as well. Let me see what's the back side on? I wonder if the back side's got a problem like this. Six sort of is that way. Six, they say he used 8 sheets of newspaper. So the area is already described as 8 sheets. So this right here, this is the area of the smaller one. And it says that he wants to make it, oh, but no, that's a volume one. That's not an area. I was thinking flag at first, shoot. Oh, 10. 10 works. 10 works like this. So they've got a cylindrical swimming pool like this. And the original swimming pool has a volume of 1,200 gallons. So that's a volume, so that's the third power. So we've already calculated this by taking a number, in essence, times another number. We've come up with, we've used a radius squared to get the area, and then we've used the height times that. So in this case here, here's your radius, here's your height. In order to come up with that 1,200 gallons, they did something like this, pi r squared h, and then they turned it into gallons. So they did a unit conversion. So this right here is the volume itself. And if we wanted to make a similar pool with double the radius, what's going to end up happening is that we're going to have to multiply the radius by 2 in the next pool. Maybe this one doesn't do it either. So then we either do this. We either say the new pool is going to be 2r quantity squared times h, or we can just say we've got pi r squared h, and then we're going to multiply this by 2 squared. Because we're taking a length that gets used as the, in part as the area of the surface, and it's being multiplied by itself. So if we're making that twice as big, we have to,
Why does the 2 have to be squared?
because this portion of the formula is dealing with the area of a circle. So we have k squared. And so all we're doing is we're changing this part here. If they said we're gonna double every dimension, if we're gonna make the radius twice as big and the height twice as much, then we'd have a 2 twice, and then times the h would make it a third time, that'd be a volume.
Well, aren't you multiplying the whole thing by 2 on the second one?
No, because if you multiplied the whole thing by 2, you would just be doubling the volume.
Right.
Here we're doubling the size. So let's say we draw this thing out. So this is now 2r. The r is made twice as big.
Right.
We still have the same height, so this volume is going to be equal to pi. That's your radius.
Okay.
Because imagine if r is equal to 5, then this is pi times 5 squared times h. And here, it would be pi times 2 times 5, which is 10 squared times h.
Okay.
So I think when we do these problems, we have to decide whether what we are being given
But then how would
It's-
you get how many gallons?
well, how many gallons is that? So did you work to this one already?
No.
Okay, so now we have formulas, right? Is that right? Okay, so let's, let me clean this up a little bit. So the original formula says that 1200 is equal to pi r squared h, correct? Okay. Now we do not know the new volume. So that new volume will be equal to 4 pi r squared h. Because instead of just taking 2 times r and squaring it, I pulled the 4 out front. So if we look at, if pi r squared h is equal to 1200, 4 times pi r squared h has to be equal to 4 times as much. So I have to multiply both sides by 4. It's going to be equal to 48. Yeah?
Okay.
There's a lot of proportional thinking that goes into this lesson. And identifying, what do we really, what do we really change? Are we changing a length? Are we changing an area? Or are we changing a volume? Even though this is talking about a volume, the only part of where that volume came from that changes is an area calculation. If the problem said the pool has twice the radius and twice the depth, then it would be 8 times. Because you'd have to take 2 times the h and 2 times the r, and since we square the 2r, we get 4. And then the 2 from there becomes h. So who's done with everything? Good. You should work on this. Talk with one another about them. I think that's more valuable than me just going through. I think I've said almost everything that I need to with this at this juncture. So let's do this. Let's spend some time working on it. You have a half hour. And we'll probably save triangles for Friday. And just get them started and finish them on Monday. So track people, we're gonna start triangles on Friday, work a little bit in class, and we're gonna finish them on Monday. So we'll see you for some of that as well. I'll record that one.